Mr. Azizam Helmi from Physical Clusters. He's the PIC for ICP OES. I think he's more than 25 years, almost 25 years in handling laboratory equipment, including ICP. Together with us today also Madam Katrina Ng Swileng, our guest speakers, whom is also experienced in handling testing and also including the ICP OES. So already 3 o'clock, I will begin this webinar. So this is our guest speaker. You can see from the screen, Madam Katrina Ng Swileng. She's the chemist. Our guest speaker, me myself on the right picture, and also Mr. Azizam Helmi. Today, the title will be title introduction will be the ICP OES or inductively coupled plasma optical emission spectroscopy overview of sample testing. And then I will introduce you to Central Analytical Laboratory, UTP, and then we have our CAL corporate video, and then we go straight away to the what is ICP OES, and then the next title will be ICP OES, a workflow overview. Later on, Mr. Azizam will add on how the ICP OES will begin with the process workflow. And then we will go to the how the plasma is injected for the ICP, and then ICP OES versus ICP MS, what is the difference? And then the last part of mine will be the interesting facts about the ICP OES. Okay, this is the introduction to CAL Laboratory. We are providing services. Then the committee was the director itself. I am Muhammad Fatimi Izzak bin Khamis. The chief editor is Mr. Imtiaz Amir, or the CAL manager. The editor is TS Naim Imatuhani, Naina bin Muhammad, and chemist Nur Hashila Muhammad Amizi, our chemist, and myself on the right. So the other members is TC Asnizam Helmi Talmizi, Puan Faizah Muhammad Isa, and also Encik Omar Ramli. Moving on the right is TC Irwan Osman, Mr. Johan Arif Muhammad, Miss Isyawati, TC Muhammad Anwar Abdul Muin, Puan Nurul Husna Muhammad Muhayyuddin, TC Surya Adam Dina Tomo, Mr. Jarani, and also Mr. Muhammad Hazri Ahmad Syafin. So all these PIC in the laboratory will be introduced later on via CAL corporate videos. Okay, for your kind information, we are accredited in 17/05/2017 for the water scope, which is drinking water or potable water, for the determination of metals, silver, aluminium, arsenic, boron, barium, cadmium, chromium, copper, iron, manganese, nickel, lead, selenium, and also zinc. The standard use are APHA 3120B and also APHA 3030F. Then our list of approved signatories, chemist Nur Hashila binti Hamizi was also in this webinar today. She was the technical manager, also chemist, and also chemist Puan Nur Siti Fatimah binti Arif Shah. So this is our location, CAL Lab Laboratories in Block P, UTP. I will begin with the what is ICP OES. ICP OES is inductively coupled plasma optical emission spectroscopy. Is an analytical technique used for detecting our chemical elements for any sample sent. Then for the first time sample sent to the laboratory, it will be monitored. We will check first whether it is suitable for testing. Then it utilizes a plasma source to excite atoms and ions in the sample. These excited species emit light at characteristic wavelengths, and the emitted light is measured to determine the element concentration. You can see on the right side how the QC is running. Is for your example view. Then what is the plasma sources? How it works? Emission from atoms and go to the plasma sources and will go through the sample. It uses a plasma source to excite atoms and ions in a sample. Excited atoms emit element-specific wavelengths of light, and then intensity of this light is measured to determine the concentration of elements. And then what is the application for this ICP OES? The application will be environmental testing, for example, water and for soil, and then metallurgy and mining. Next is pharmaceuticals and also petrochemical analysis. ICP workflow, this one is more on technical part. Mr. Azizam will later on explain that in detail. The first step is sample collection, whether it is solid, liquid or digested material. And then for second step is sample preparation, including filtration, dilution, acid digestion. And then we need to do the calibration, external standards or internal standards, uses blank and quality control samples. Then for sample introduction, nebulization via spray chamber into the plasma, and then plasma generation. RF coil generates argon plasma to excite atoms, and then emission detection using the optical system splits the light to detect the element with specific wavelengths. And then the next stage is data analysis. Software quantifies element concentration versus calibration curve. And then the last part will be the reporting of our final results. Final result is reported in ppm, ppb, or mg over L. This is the workflow overview. First step is sample preparation. Samples are digested or diluted. And then for the sample introduction, a nebulizer converts the sample into aerosol, or we can say spray form. And then for the plasma generation, argon plasma is used to excite atoms, and then emission detection, optical system separates and measures emitted light. Number 5 is the data analysis, which this is the stage where we produce the final report. Light intensity is translated into concentration values. Then from the reading, then we translated it to a report. Something like this. During we are doing the results, you can see on the right side. And then how plasma generated. Let me try again on the video. If no sound, then I will provide you the link later on. The first thing is the sensitivity and also the detection limits. For the ICP OES, the detection limits in parts per million or ppm to parts per billion compared to MS, much more sensitive, detects down to parts per trillion or PTT. And in terms of elemental coverage for the ICP OES, it's good for major and minor elements, for example, Ca, Mg, ferrum, and Al. Then for the MS, deal for trace and ultra trace elements, for example, Pb, U, Cd, and As. For the speed and throughput, OES is typically faster for multi-element analysis with higher concentration compared to MS, might be slightly slower due to ion focusing and quadruple scanning. Okay. And then for the application terms, the environmental, metallurgical, industrial, food safety for higher concentration is for more on OES. For the MS, more on pharmaceutical, clinical, environmental, nuclear for ultra-trace analysis and isotope radio ratio studies. We move to the interesting facts about ICP-OES. Hotter than the sun surface, the plasma in ICP-OES reaches temperatures of almost 10,000 degrees C, which is almost twice as hot as the surface of the sun, approximately 5,500 degrees C. And then each element has a unique light signature. When atoms are excited in the plasma, they emit light at specific wavelengths, like a fingerprint, which allowing the instrument to identify and quantify them. And then it detects the invisible, which can detect metals at parts per billion or ppb levels, which is like spotting one drop of ink in a large tanker tub of water. And then multi-element analysis in minutes. It can measure about 20 to 40 elements simultaneously in just a few minutes, making it one of the fastest techniques for multi-element testing. The purpose, ICP OES is used in water safety testing, food and agriculture, pharmaceutical, quality control, mining and metallurgy, and also
get
yeah.
Anything beside this drama and sessions?
Pardon again?
CMS cannot see.
Mm-hmm.
From which samples?
Sample will later on, we will share with you with the expert and also the technical part. Okay. Okay. And even also material analysis, and then for the big, it's a tiny sample, big data, only a few millimeters of liquid are needed for analysis. Yet the result can reveal a complete elemental profile. For the environmentally important, many countries use ICP-OES to monitor heavy metals like lead, mercury, and arsenic in water and soil, helping protect human health and also ecosystem. So it's almost 3:30. I would like to invite Madam Katrina. She's more experienced and also knowledgeable in this ICP OES handling and overview. Madam Katrina, may I pass to you?
Okay, thank you very much. So will you want to unshare so that I share my slide?
Yeah, please.
Okay, let me share. All right, everyone can see the slide.
Yes, Madam Katrina. Yes, we can see.
It's just I haven't now I'm doing the view.
Okay.
Okay.
Yes.
Yeah. So you see the full screen now? Yeah. Can
Yeah,
I?
yeah.
All right.
Yes,
Can,
can.
can.
Yes.
So thank you very much for inviting me for this short session, about 45 minutes. The topic given to me is more like sample type in the meta-analysis. I will cover this topic, acid digestion method, and then what is a matrix effect and calibration strategy. And of course, the last one is the highlight of our services that PerkinElmer not only provide equipment, we also provide the metabolic validation. But because the topic is 45, we need to cover a lot. So I only able to give you an overview in meta validation, what you're supposed to do. Okay, without any further ado, let us start. So you see, in the atomic spectroscopy analysis, you can be running all this kind of sample. Sample type can be from oil, in the Petronas, we say the oil, lubricant oil, or your raw oil that haven't processed until that maybe some of your product is a plastic. You also will be kind of your sample that in other industry, there may be a pharmaceutical, food industry, palm oil, and then maybe geology also. That means the sample range is very wide. Can be from a simplest like drinking water until a very complex sample. So all this, as long as we can convert them to there are two types. Some is that you don't need to convert to the liquid. You will run it in the solid form. And then one actually is you will need to convert them to become liquid form, which is to aqueous. Then you were able to run. Even the metal alloy also a part of our sample. Plastic, rock, soil, plant sample. Right. So in overview, if we talk about spectrum of food, here will be a spectrum of your sample. So that means you see underneath at the bottom, that is the simplest way to digest the sample. So if you have a task or project to run all at the bottom, I will say congratulate. There is a very simple method to run. Of course, the top highest is to digest the diamond. Not carbon, it's a diamond. So and then when you're at the top, your sample is a bit harder, right? So you will need to have a HF to digest. Even let's say you have a plastic, they are considered big molecule, so it's difficult to digest. And then another one is because all this plastic, they have a high carbon, like grease, fat, they have high carbon. But if we say the lubricant oil, normally we would like to have okay, when we go through this topic, is that not necessarily every time you must get your sample to digest to become aqueous, because if we are lubricant oil analysis, we would like to avoid doing digestion, because digestion always will have a very longer waiting time in the sample prep. But in the lubricant oil or palm oil, for the analysis, we are doing a dilution. We dilute with the solvent. So not necessarily you would like to convert it to become a liquid aqueous form to run. But if those cannot, like you see the coal or the plastic or the alloy, so we had the alloy or we had to actually no choice in the mean or no choice, then only we had to digest them. Okay, so if we look at the geology in a particular way, because mineral or those geology sample, we actually have a two type of way of digestion, two type of preparation. So of course, all rock sample first they must ground to find this size. Then we can actually digest. We can use a microwave digestion, or we actually can make it to become a fusion big. So that means fusion, there are many type of fusion flux that in the market. So this is one example. Not necessarily you must use a lithium beta borate. So you can have other type of flux. Basically, you make it become glass. So when you introduce, this is the thing that you introduce as a solid. That means you are making a glass bead to go to the SRF, to the X-ray. All this is actually solid sampling. In fact, also from the fusion bead, you also can go to the ICP-MS. ICP-MS. So that will be a laser ICP-MS. So like in JMG EPO, they actually have 2 units of, they already make the fusion glass bead. Because SRF only can run percentage, but just now the previous slide that you already had some concept, ICP-MS is actually low level. So that's why they are same fusion bead they already do for the SRF. They also use a glass bead to actually introduce to ICP-MS. At this time, ICP-MS was received the dry aerosol. Like just now is a good introduction because you already have some concept. So laser will be our auto sampler. You know, you have a very expensive auto sampler. You know, when you couple laser ICP-MS, ICP-MS is cheaper than the laser. That means your laser is much more expensive compared to ICP-MS. So have a laser will be the one that embrace the glass bead to uh, to create the dry aerosol, and then they carry by the carrier helium gas to introduce to the plasma. So it's a plasma, but in front of the equipment there is no spray chamber. It's just a tube, transfer tube, where transfer the dry aerosol to ICP-MS. So there is JMG have two set of this, right? So this is what I actually just now forgot to put this slide for you to see. So when you were actually using the same glass bead you introduce the ICP-MS, then they will call in short. If you go through a lot of those paper, people write. So if you see LA ICP-MS, is mean to say that what I actually mentioned just now is a laser ICP-MS. So this is called the solid form. You introduce a sample in terms of solid form, and then the good point that you actually kind of make a glass bead, you actually homogenize your sample, because in terms of geology, even your rock itself, because I'm not a geologist, the rock got a lot of name on, and different type of different type of name. So when they actually make it to become glass bead, they actually homogenize. Any type of rock, different type of rock, they already homogenize, become the same background. All right. So that will be overview what is the sample type. So that's why in terms of inorganic analysis, you have no way to run away from the sample preparation. So actually the whole error, if you, let's say you introduce a solution to the ICP, most of the time your error already, in the instrument part, your error already reduced. But at the front part, it's very important that to have a very good sampling, right? Your sampling should be representative, because sometimes your rock is very big, but at the different area of the rock, maybe their concentration is different, right? So they say ground it to become powder, and then the homogenization will give you a much more reduced error. But the sample prep in the laboratory part, not included the sampling and transportation. The laboratory people will actually consider crushing, weighing, digest, or dilute it to the volume that you want, then only get ready for analysis. The error is reduced after that. So most of the time error is actually at the front part. Right. So in terms of analytical analysis, you can have I think this one is already not so big deal. I already have the flow of them already mentioned just now. But what are the problem that when we want to do this, we must ensure that homogeneity is there. Our sample of very little must represent the big one, and then your calibration curve will need to be represented, because sometimes your method, whatever method that you want to do, you must have your reference material to actually represent you. If you don't make it become a homogenized metric. Just like I mentioned that, let's say I have a, geology, I did give you a geology, just said you have a sediment, and then another material is actually calcite. So calcite and sediment, they are different metric. So if we don't want to homogenize them to become a similar metric, we will have a problem in terms of calibration curve. So if I make even the fusion bit, I just compact them, become a compact. Sometimes when you say bit, people will make a compact bit and rather become fusion bit. But these two actually, the more benefit, more we will say that better homogeneity is actually you become fusion bit, because when you become fusion bit, your background is only the glass, lithium boron, it's a glass. But if you actually compact only, calcite actually and other material, they are different. So you need to find a calcite reference material to plot the calibration curve. I hope you understand that, because if we want to say, I don't want to have sample prep, Katrina, you keep telling us, oh, I got a lot of sample prep, I need to do this. I want to be direct. If I have this powder, I want to compact it, and then I run. Also cannot. We have to make it always must think of when do the calibration curve must be presentative, right? So then, because if you have different type of background, actually, which is later part, I will tell you, your background will cause a different type of interferences. So that's why in terms of microwave digestion will be similar like a fusion bit, but fusion bit is actually your process is a bit longer. So now we combine, we need to still have a sample prep, but you use the microwave to digest. You have you decompose using microwave, and then this become a solution that is actually harmonized. Everybody had the equal background. So then you actually can run them in the same external calibration curve, or else calcite and other type of rock is not the same material. Right? So of course, when you combine, you will say, oh, time consuming, and then handling step, use a lot of acid. I did not put on all, actually more acid had to be used, and then knowledge of the digestion had to be there, because if you use a microwave is just giving a wavelength to let the medium absorb. What is your medium? Your acid to absorb and then actually rotate. That is what the microwave do. Actually, the art of digest a sample fully is actually in your chemistry. You need to know, oh, this rock, they are high in tin. Oh, I must use a HCl to digest. So if this sample, I would like to study about the gold, then I must actually put the HCl for them to dissolve fully. So if I'm going to run rare earth, or majority of the rare earth, they like nitric acid, I must have a nitric acid. So the problem, I actually now did not list all. Just now, whatever I mentioned is all the problem when we want to digest. Our knowledge also must be increased, right? Right. So that is what I want to highlight. Even though that we say, we need to decompose, whether it's in term of glass bead, or we want to make it using microwave, we have to also consider all this. So if we say, maybe I don't want to invest in the microwave, I want to use a hot block to digest. Then now we compare between microwave digestion to the hot block. And the hot block is more time consuming, because in the microwave digestion, you already time consuming. It will take up about 1 hour for you to actually weigh your sample, and then put the acid, and then you close the vessel, and upload into the rotor, and then digest, then mark up. So that will be a time consuming. But if you use a hot block, because you cannot pressurize, because when you use open digestion, you are no pressurization, so you actually cannot shorten your digestion time. Your decomposed sample digestion is actually longer. So maybe it will take you 3 hours is already, I would say I discount. Maybe you will digest for the whole day, even the sample will not be able to digest because it's not pressurized. right? So now if you go from these two comparison, if you go for the microwave, and then what will you want to have in the microwave system? So in the microwave system, you would like to have at least this bullet point in your mind. So you want to have a control when you doing the digestion. So at least one parameter, if you microwave can control the temperature or can control both temperature and pressure. So the meaning of control is not monitor. So don't forget that if you put a probe, you only monitor. The meaning of control is the temperature had to feed back to the magneton. Magneton will need to regulate. Don't put too much of energy, wavelength energy anymore. And if your pressure is too high, the magneton also know to adjust, not to give a lot of energy anymore. Right? So you, of course, you want to have a flexibility. Just now I give you a spectrum of the sample. So you would like to, hey, sometimes I'm going to digest a simple matrix, which is at the bottom. And then sometimes I want to digest a difficult sample. So you have a choice of same oven can insert different type of rotor. So you want to have a high throughput. If I'm going to be a commercial lab that run a lot of sample, so I will need to consider high throughput. Yeah. The ease of use is also very important. You want to be very complex equipment, many steps. You want to have A, B, C, 3 steps only. And then when you use, you want to be safe for yourself and also safe from the environment. Yeah. And any microwave actually come with a scrubber, because every time you have a fume hood, before you actually release the acid to the environment, your scrubber is already neutralize the acid fume. So the microwave has a scrubber as well. You want to consider that also. And then you want to have a system that have a very low cost of operation. Whether they only warranty the oven, will they warranty your vessel? So you have to think all this in your mind. So will you want the supplier of the sample preparation and the equipment is also a same vendor, because you have to know that your sample, your methodology consists of sample prep or decompose of sample and then continue by analysis. So if you got two part of the method divided two part. One is preparation, one is the analysis part in the equipment. So if you're under the same window, you want to troubleshoot, it's actually much more easier. Because if not, then one party supply just the equipment sample prep, another party is the ending the analysis part. So the game will be ding dong about these two vendor. So PerkinElmer is the only vendor we supply from beginning total. That's why my title is a total solution, beginning from sample prep analysis until method validation. That's why the last topic is the method validation. So now our microwave that we supply, the name is Titan MPS. The model is the latest model is 320. So there actually you can see that same type of oven that we have 4 type of rotor. Okay, in terms of the vessel design, we actually have the closed vessel. Yeah, at the bottom here is a closed vessel. The white one, all Teflon, that one is all closed vessel. And then the closed vessel, we got 2 type. We have high pressure type with a high productivity type. And then in terms of the top one is actually your venting vessel. That means if you got high pressure, there is a spring cap to release the pressure. So we will say that this is called the venting, auto venting vessel. So auto venting vessel also got 2 type, 16 vessel and then high throughput vessel, which is 32. And then inside this high pressure, you also have a mini insert, make it become 24. So because you got 8, if you have a mini insert, the insert like test tube, but Teflon test tube, so you become 24 sample. So we are the only vendor. We not only you give you warranty on the oven, we also give you warranty on the vessel for at least 1 year. So and then another unit is you have 2 type of control. So because the microwave, a lot of time when you hear people buy microwave, they will say, hey, don't buy. Microwave can explode. But we won't. Why? Because we had 2 control. We had the temperature, direct temperature control, which is this universal. A lot of people already have, but we add another one. It's called the direct pressure control. So that means all the temperature and the pressure will feedback to the magneton. So ask the magneton to regulate the power. Don't continue to give if the sample already have a inside when you during the digestion already high pressure or high temperature. So please stop. So this is called the control. But if you monitor, you don't feedback to the magneton, this is not a control system. So we have a film collector, meaning to say inside the oven, when during your digestion or anything happen, your oven will not have any single drop of acid, will not have a film or acid, because everything we collect and then we neutralize them before we actually release to the environment. So of course, just now I already mentioned the total solution of packing armor is a single window for sample prep until analysis. So this is very important. So remind again, the control on the microwave is very important, DPC and DTC. So these are the two features that we have. So if we control the temperature, it's actually temperature is from the bottom. So basically we select a IR region that this signal of the IR signal is porous to the, do not see the Teflon. That means they penetrate the Teflon. Then you measure the actual temperature of the sample. So we do not measure the surface of the Teflon, because the signal region that we choose actually is we won't. We don't see the. It will 100% transmit. We will not see the Teflon, but we measure the actual sample. Then about the DPC, direct pressure control. So direct pressure control, we are different from people. We are cordless. You see, it's actually the cap. So we make the cap a special cap. So this special cap had the prism, had the polarizer film. So they have a signal at the cover of your oven. So when the pressure is not there, the light from this oven will actually light is come from the top. Then this is the detector. The light from the top actually was seen by the detector 100%. But when your pressure is there, so this what we say this glass ring will be moved by the pressure, and then will make the polarizer prism here will be moved up maybe in 1 mm distance. So actually when you move up 1 mm, the light actually from the top do not seen by the detector, and then this is how actually the microwave know, oh, now during the analysis time, during the digestion time, the pressure already built out. So we will need to control the pressure to be released. So this is how we actually do the direct pressure and then direct temperature control. I think another two slides is all much more detailed. So where is the thermometer put at? Is at the bottom. So every of your vessel, let's say I have a 16 vessel in the microwave oven, every 2 seconds, your sample will be measured. I mean, now it's the sample vessel number 1. So the 2 seconds later is vessel number 2. So all of them will feedback to your magneton to tell the magneton how to regulate the magneton's energy. So and then this slide is telling you, just now I say the signal that we choose for the IR thermometer is actually porous to the Teflon. So we do not actually measure the surface, but we measure the actual sample temperature. And then if you look at the those pharma, they will need to actually have an NIST standard to actually doing the PM. So our engineer will bring the NIST standard to actually go and calibrate at the 200 degree, because if you use microwave digestion, your sample should able to digest at the most common digestion temperature is 200 degree. So that's why when you do the calibration, you also check at the 200 degree, plus minus 1 degree. And then the pressure control, just now I already mentioned, but I want to highlight again, we are different from others because we don't have a probe. You do not need to buy a probe. You actually will not have the breakdown. The polarizer film is only a film that you need to stick, just like your handphone. You have a sticker to actually stick the polarizer film. So the prism will not spoil. The ring is just a glass ring. It will not spoil or unless you go and drop on the floor. So actually, if you compare to the probe, normally the pressure probe, we use for a while, maybe you need to change. But this is actually more like a broke proof DPC cap. The only thing is a polarizer film. The film is actually already included into your PM package. So whenever you have a PM, our engineer will stick another polarizer film for you. And then one box of polarizer film is only a few hundred ringgit, and then they got 24 pieces. So it's not an expensive probe like other people, but we can do the fantastic job with a simple but advanced that no contact. So you actually, even in your first vessel itself, you also will put your sample, and then your probe is not contacting your sample. You know, when you have a probe, a lot of time other vendor, when they had a probe, they will force the customer to use a lot of acid. Let's say, for example, remember at the bottom of the platform of the sample, plant sample is very easy to digest. For in my microwave, I use only 5 ml of acid. But because they use the 5 ml of acid, the probe is not immersed in the acid, then they forced to do 10 ml of nitric acid. You see, the acid content become double. So that's why I want to highlight to you all again. So using a probe that you have to have a consideration of, you might need to change your probe, and then you use your acid consumption will be actually almost double. Right. So and then in terms of auto venting vessel, which is a spring cap, when the pressure is built up, this spring cap will open and then release the pressure. Same like other. But we are doing differently compared to others. We actually do it right. What is called do it right? So we actually on the cap, we put a Teflon tube. So if your sample actually had high pressure, so you know when you digest 200-degree, the acid film, when you the spring open up, acid film will actually pass through this Teflon the tube. So this Teflon tube, and then this is hot, yeah, outside is cold, definitely you will see a condensation. So now as a chemist, why I say do it right, meaning to say in the 16 vessel I put, I will definitely know which vessel actually already venting out, which vessel do not actually have a high pressure. That means the spring cap is not open up, but your digestion is actually complete during this digestion. So if do not open, that means when they do not open, then you are very assured. Why you assure? Because when you open, you cannot guarantee your mercury is volatile. Will they go away together with the acid film? When your pressure high, you open up, it will also go up. So now as a chemist, when I see there is a condensation in this Teflon tube, I had the choice of reducing this sample a little bit more. So if let's say I start up with 0.5 gram of sample, and then I observe when I do the digestion, the venting up is already happening. Yeah, because why? I saw the condensation. So venting out already happening. So I have the choice to reject. I don't want this sample. I don't want the markup, but I want to repeat this sample with the sample 0.35 gram. So when the sample is less, your pressure will not build up so much, then you will not actually venting off. So this is what we do differently compared to other vendor. So we also at the end of the hose, we also had the NOx. When you digest sample, you sure will have nitric acid. So we put the NOx sensor. So also will tell you when you complete the digestion, the sensor will tell you, I detect your acid gas or acid film already. So the moment you detect, you need to observe already. If they do not say, because after the completion, the software will show I completed. If they don't give you any signal of this NO sensor detected gas, then you don't need to observe anybody. But if you see the sensor already mentioned, then you observe every of these 16 16 Teflon tube, you observe it, which one actually already venting out. And then that sample, you had the choice to reject or to continue sahaja. All right, so the choice is at your hand. So again, we would like to tell you that our vessel got two types. It's actually up to you. So permanent seal vessel is the one that it promoted by a lot of international method. Like for example, this is a pharmaceutical method, USP 233. They already spell clearly. If you want to digest sample with a microwave, please choose the microwave, have the closed system, closed digestion system. That means during your digestion, nothing actually open up. But venting vessel, you already know, the name is called venting. If I high pressure, I will release out the pressure by spring cap open up and then will release through the, this at the center here is a gas manifold. So you see, when we release out, other people venting vessel, when they venting out, venting to the oven, yeah, went to the environment. Then later your electronic bulb all corroded. But for us, if we venting out, we went into the gas manifold and then we neutralize them before we release to the environment. So same for the closed digestion system, because why we still need to stand by even though they are closed system is sometimes when you digest, one of the sample is very aggressive. Yeah. So what we do is we had the seal and the ratchet disc to actually open up to release it to the gas manifold. Again, anything happen, your oven is always free from acid film. This is also protect your electronic part. So I think that's what I really highlight. So we have the choice that as a chemist, if we observe the Teflon tube is already had the condensation, we can actually we can start up with a very high weight, but we can reduce it later on. Yeah. So this is most likely different type of vessel and then suitable for which type of client, which type of industry, and then what are the temperature, what are the pressure. So if you're venting vessel, you enjoy the pressure of 20 bar. So this you will enjoy the pressure of 40, and then this will be, yeah, your sample has less 8, but you enjoy high pressure system. Okay, so we are the only vendor that we actually promote environmental friendly. We would like you to actually, all the acid fumes should be collected at the gas manifold, and then before you actually went out to the exhaust, so please neutralize them. So we have a scrubber behind the equipment. So this is a caustic stone. Then it will neutralize. Then after that, you go out to the environment. The gas is already acid free. Okay. So for the environmental purpose. So now you see when you decompose the sample, so you actually minimize your metric effect. Yeah. But the whole overview, you are actually, this is like a slide that I conclude the microwave digestion. So you convert the solid to the liquid. You minimize your, of course, the metric effect. You destroy your metrics. Yeah. What is a metric like? Let's say I have a grease. When I digest with the microwave, the carbon already gone because all the carbon becomes CO2. So this is the meaning of you destroy the metric. Let's say I am actually, I think that is a better, the good example I can think of lah. Destroy the metric, it means the carbon no longer there. So of course, a good thing is you actually make them same medium now. So you from microwave, your sample markup is already aqueous, your standard is also aqueous. So both of them are the same form. Yeah. And then you during the digestion, you also already homogenize your sample. So this is a conclusion we make from the topic of the sample decomposition. Okay. And of course, you want to go more detail, pro and con. I think in your mind, I already mentioned some, right? So you actually, your good point about the digestion, you give to a more representative sample. Yeah, you reduce your problem when you come to the AA part, come to the ICP part, and MS part is actually reduced. You're easy to plot into the external calibration curve. Yeah. So then, but poor thing is actually you actually much more labor. Yeah, you have one more extra process. Your bottleneck is always at the digestion part. Of course, when you digest, you risk of the contamination, or you risk of losses when the venting is happening. Your analyte also go out together with the acid film. So that is we make a conclusion so that you're aware of this. So that will be the first part. So now when you come to the equipment, you already harmonize your aqueous, your sample is aqueous, standard is aqueous. But when you come to sample to the AA, to ICP and ICP-MS, all of them have the sample introduction. Correct. So when you have sample introduction, AA, you had the nebulizer. This is graphite. So AA, you had nebulizer. ICP, you also had nebulizer. You had the sample introduction, cyclonic. Here, you had the nebulizer. You had the cyclonic spray chamber. So meaning to say, you need to make aerosol. So if your sample have different viscosity, so this, I try to find the image of viscosity, look like this. That means high viscosity or low viscosity sample is called the physical metric effect. It's different effect. During my calibration curve, I have 1% or 2% nitric acid. But if my sample, the viscosity is actually much more thicker, much more higher, so I will make different type of aerosol, which is I also explain later on. Or sample have much more other thing, like seawater, you have other thing. So this is a first thing that we had to think of when we come to ICP or at the equipment part. So the second part is your spectra. So that means will I have an overlapping or not? Yeah. So this will be called spectra. If I run ICP-MS, do I have what type of overlapping in ICP-MS? Then in terms of chemical metric effect will I have a sample that is a double bond? I have a triple bond. I have a 4 bond chemical bond, which is much more difficult. So normally chemical effect will be much more on the AA, because AA is the one that their temperature, just now you already hear, the plasma had 10,000 Kelvin. Plasma had 10,000 Kelvin. The only thing in AA, in the graphite, you only 2008. In the flame, you only 2005. So whatever that you want to run, you must able to make them become free atom. So if you have an analysis of like silica, they are 4 bond chemical bond. So it's very difficult to run in the AA, but very easy to run in the ICP, MS, or ICP OES. So ionization is, will it happen become ion? Because when you want to run in the atomic spectroscopy here, so in AA, you must maintain as an atom. You cannot become ionized. So most likely, these two bottom here is actually problem for AA, not a problem for ICP OES or ICP-MS. Because in fact, ICP-MS is your sample, your analyte must convert it to become singly charged ion. So you must become ionized. But AA, you cannot. You have to stop the atom to become ionized. So the last two problem is actually problem for the AAS. So if you, as long as like I mentioned, the detail of this one, physical, let me go more detail on the physical and the metrics. So in terms of sample introduction, as long as your equipment has a sample introduction, you need to think of this way. So if let's say my calibration solution are using 1% nitric acid, I will sure have this type of flow rate. But if I had the sample have a higher viscosity, then my flow rate will be different. If I have organic, my flow rate will be different. So therefore, you cannot say that sample organic, I use the aqueous calibration to run. It's not. So if you're organic, let's say just now I said palm oil, they just they dissolve the sample in the solvent, and lubricant oil, they dissolve the sample in the solvent. They will use a calibration curve is also the same type of solvent, so that you have the same type of flow rate. And then once you go to the nebulizer, you will form same type of aerosol formation of the droplet at the same size. Because in the sample introduction is, if you become big droplet, most of the time you will go to the waste. Like in the ICP, all the big droplet, all an MS, all the big droplet will go to the waste. So you want to try to make the sample and the standard have the same impact. So you don't want it to have different, because different you will have a bias. So most of the time, if you are AA, you will use the method standard addition to overcome this physical and matrix effect. But if you are in ICP MS and ICP OES, then the way you correct it will be either you use the internal standard. So internal standard you can use online or you use offline. Online, that means you will have a T-piece to join the internal standard and then mix with your sample or mix with your blank or standard and go to the nebulizer. That is called the online. Offline, you will tedious. You will add one by one, add to all your calibration blank or all your standard and all your sample. You need to add accurately. If not, then you're going to do the correction will have an error. So if you do the method standard addition, in ICP also you can do the method standard addition. So the software will actually do correction automatic for you. After you complete the analysis, your calibration curve will look like normal, but please be aware that during building out this calibration curve, this standard 1 or standard 2 already had the impact of the metrics in the calibration. So this is the highest quality. That means your calibration curve have the same type of metrics, you have it in your calibration curve and sample. So that means the quality of the result will be bad. Very good. So sometimes I use two. I use the meta standard addition plus the internal standard. So it's double quality. Okay. So of course in the ICP OES, what is called the spectra, that I will explain both OES and MS. So spectra will be the overlapping. So like for example, in this window, you can see that this vanadium, chromium, moly, they are very close to each other. So you see a very noisy peak around let's say you are running vanadium, but a lot of noisy peak beside. So this is called the spectral interferences. So in ICP, actually, there are two types of the spectral interferences. Either whatever you want to run, let's say what you want to run is the orange color. So this is the peak, but your interferences is hiding inside the peak. So you look the peak, when you examine, you look the peak, it's very nice. Nothing happened, but it's already hidden inside. So this is called the direct overlapping. So direct overlapping, you have to use the inter-element correction, which is the mathematic correction. And non-direct overlapping, which is your analyte is this orange color, but your interferencer is this blue color. So that means you can still see the half of the peak. And this, you can use the multi-spectral fitting, which is called the image correction. Multi-spectral mean we will like you let the software learn the algorithm of how the interferencer look like, and then it will actually erase off the interferences. One is mathematic, one is called the image correction. Right. So in MS, you got three type of problem. Either because MS you are running isotope. So for example, maybe I give you some idea first. When you run copper got two isotope 63 and 65. And then the isobaric mean, let's say you look at the zinc actually have about four type of five isotope for zinc. So this is the most abundant zinc. But in terms of isobaric, is mean zinc had 64, nickel is also 64. This called the isobaric interferences. Then if you look at the, when you run ICP, you got argon. Argon is 40. Calcium is also 40. So this is called the isobaric interferences. The one that same mass, same atomic mass with us is the isobaric. So in ICP MS also, you got the second problem is called the polyatomic interferences. So the metric effect, contoh example, you run seawater. Seawater, you got a lot of chloride. So you got plasma. Argon plus the chloride is actually 40 plus 35 become a problem for arsenic. Let's say you run the HCl. then your sample got HCl, or you digest with the HCl. So HCl got chloride plus the water, you dissolve in water, you got oxygen. So this 35 plus 16 become 51. When you run vanadium in the ICP-MS, you will have this. So let's say you run rare earth. So rare earth, they will actually interfere each other. GD is a rare earth also, but it's a low rare earth, lower rare earth. If GD combine with hydrogen, they will be interfere the TB. GD combined with the oxygen, it will become a problem for the heavy rare earth. So this is an example of the poly. So this is second problem for ICP-MS. First problem, isobaric. Second problem is when they become a polyatomic, they combine, they become problem to us. And then the third one in ICP-MS is called the double charge. So double charge, it means because in ICP-MS, you supposedly you must make a singly charged ion. But if the plasma is too hot, then you will become a double charge. So that means you overdo, you become double charge. So double charge means your mass AMU divided by 2. So let's say ND is 150. You double charge, you divide by 2. So you become a problem for arsenic. So samarium, you divide by 2, you become arsenic problem. So GD, you divide by 2, it becomes selenium problem, and so on. So this is called the metric effect into the ICP-MS. So ICP-MS got 3 types. So of course, if I tell you the background challenges just now, isobaric, polyatomic, and double charge, now you are actually, if you're doing the rare earth project, I'm going to tell you the most difficult application so far as a porous specialist, the most difficult application is actually rare earth. So because rare earth is a lot of what is the behavior of rare earth? Rare earth itself got a lot of isotope. GD, you see the pink color is all GD. Then ND is a lot isotope. So if you are multiple isotope, then you are going to become a polyatomic in the future. That means you are so many isotope, you add oxygen, you become polyatomic, you become a problem for your elderly rare earth. That means for your heavy rare earth. So if you are samarium, you see, samarium is the red color one. Samarium got so many isotopes. So it's as long as samarium become oxygen, then they will come to the heavy interference to the heavy rare earth. So you see in the heavy rare earth, we got 4 elements. It's very poor thing. So because sometimes when you have overlapping, you can run away. Like just now the ICP OES. If this wavelength you overlap with me, I can use other wavelength. But you see, TB is monoisotope. I have no way to run. If you interfere me, I have to think of other way to actually overcome. HO is also monoisotope. TM is also. YB is actually, they had 2 isotopes, but this isotope is no sensitivity. So you had to choose this isotope to run. And then if you got problem from here, and then GD become oxygen, will be problem for your YB. So you see, because GD is a lot. So this not a very simple background challenges. So in rare earth, normally is your heavy rare earth is the one that actually a difficult element to run. Of course, how you overcome? So you must able to filter and filter and filter. The more you can filter, the more you actually can clean up your background. So the latest model is our Nexion 5000. We have actually 4 quarter pole. That means Q, 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 Q. If you look at four is 4 handphone, but actually it's quadruple mean we had the Q1. Then if we don't want to discount this Q, because other will say, oh, this maybe is not Q. Okay, maybe I will say the real Q. We have Q1, then we have Q2. Where is this here is a Q2. Q2 is the place where we pump in ammonia gas, oxygen gas, helium gas, or hydrogen gas to remove the interferences. And then this is Q3, but we have another Q0 actually will be the one that bend the ion 90 degree. So they mean to say, when I do the analysis, this is your plasma area, your plasma. So make the singly charged ion. You only bend the ion that you want to analyze. 90 degree. But those that you don't want to analyze, you let them go to the vacuum pump. So that's why Q1 make a fantastic work that to make sure our system is not the direct path. We actually make sure that during you are not doing this element, you please throw them away. But the time that you do this element, you are only bending in 90 degree or the analyte. So for all ICPMS, it's all sequential in the world. All ICPM is actually run one by one. So we had 3 quadruple. Yeah, first is making the first filtration. Second is actually isolate other filter off other mess. Then this one is for the interferences removal, and then this one is for the high screening speed. So every quadruple had their different function. So just now I tell you all the problem of the background. When you look at purchasing ICPMS, your mentality have to look at the how I want to remove BEC to the lowest. B is mean background. E is actually the effect, or we say background equation concentration. That means the contribution of reading from your background, you want to remove until the best lowest reading. So because we have the 4 quadruple, first filter, second filter again, so the third one filter, the Q2, which is a cell filter, and then the third one filter. So we have 4 time filtration for this ICPMS, the latest we have. Okay, then now I got 2 more topic to cover. It's about calibration strategy. So if I do not mention this to you, a lot of time people will actually plot the calibration curve as they want. Oh, I want to run the analysis. I plot 1 ppm, 2 ppm, 5, 10 ppm. So do you actually plot your calibration according to working range, or just do as what you like? Or if you, let's say you have another school of thought, they will say, I would like to have a calibration curve, have a very wide range. Maybe one in the blue moon, my sample is 10 ppm. But actually, the 10 ppm sample only come in once year, one time. But majority of the sample is only 0.3, 0.5. So why do you want to cover a high range? So because sometimes customers say, oh, I have a calibration curve, have 10 calibration point. Katrina, this calibration curve cover all. So which one is actually much more quality? Plot the calibration curve according to the working range, according to the nature majority. Let's say I have a effluent water. Effluent water is always low. Should I focus on plotting the calibration curve? The result is always low. Or I plot a calibration curve that is maybe once in the blue time, I got one sample that is high. Why not the one sample at the high there? You do a dilution. And you want all the 1,000 sample to compromise your one in the blue moon, the high result. Okay, so now maybe I give you the fact, then only you will get what I mean, the calibration strategy. So this is a real situation. This customer have a very wide range of calibration. This ICPMS, they calibrate 11 standard. They say because I going to receive sample very low until very high. So I plot calibration curve from 10 ppb to 1000 ppb. My calibration R square is fantastic good, 49. Okay, so then you will see very happy. But this is not a good calibration curve to run for the sample that is a low level, because most of their sample is 3 ppb, 2 ppb. You run in this calibration curve, you're going to have a lousy result. So because of what? This is the law. It's not the equipment not performing. This is the law of statistics. Now you enter the statistics class, because of wherever you run, you had a high curve. Let's say this is 100 ppm. So for example, that the relative error. So let's say 1% error in the 100 ppm, or 1% error in the 50 ppm. They are different. 1% error in the 100 ppm is 1 ppm. So if I have a 1% error in 100 ppm, anything at the bottom level, 1 ppm result, all were gone. Okay, because if I moved it up, this one will go down. So as long I have movement of 1% error in this area, my 1 ppm result will gone. So that's why if a customer run a calibration curve of 100 ppm, they tell me my result is 0.5 ppm, sometimes get 0.5, sometimes I get 0. Sometimes I get 0. I say, yeah, I expected this reading to happen because of the absolute error for the high curve. Actually, the power is at the high curve. So give you some calculation. So let's say this is the situation. I just put in the figure for you only. So their calibration curve of this 100 ppm had this signal. So if I just have a 1% error, you see 1% error is a perfect equipment. Normally you will say 2% or 5%. So 1% error, I already have a plus minus 950 count. So anything at the plus minus 950 count, all the lower, all were affected. I hope you understand. It's not that I don't allow. I will more advocate that people please run the television according to the working range. Don't let the power to be ruled by the high calibration point. Run according to your sample. Sample is always low. Please run low. Or if your sample ready 100 ppm, yes, by all means, run the 100 ppm calibration curve. But if you make a zoom, you look at their low point, even this R square is actually very good. You see all the low point actually is meaningless. And then this customer is very proud. I have got 11 calibration curve. So basically it's 1, 2, 3, 4, 4-point calibration curve. And then another 7 point. None of them had the power over this calibration curve. I hope you all understand. This is very important. Right? Okay, then the last point is your method validation. So method validation normally is required in the industry, where they actually are more for the compliance purpose. So either they are in the industry, because university normally you don't, but like Petronas, when they are ISO 17025, they need to comply, they need to do the method validation, or in the pharmaceutical, they have to comply, and so they will need to even do more than not only method validation, they will need to do IQOQ, they will package all them together, so they will need to have a SOP all intact, because in university maybe you run the calibration, your project, you do not write the SOP out, but we always will need to actually update the SOP, and then any update we must be using the latest one. So that is what which is cover my last topic. So then method validation, you need to do all of this, about 9 bullet point. I don't have the time to go in detail of this. Maybe in the future maybe can talk only on method validation, then we'll be able to go much more detail. So I would like to conclude the slide. Do I over the time? I don't know whether I go over the time. I will conclude with 1 or 2 slides. So procurement is not an instrument, just an instrument but supplier. We are total solution, because we supply the equipment. We also is your knowledge center where you can send your staff. One source, that means we also do other people product. So we are knowledge center. We have the training center to train you all. As long as you have our equipment with the PM, then we sell the consumable. We always update the technology, and then we are the only one also bring the method validation to the market. So we also prepare those customers who have ICPMS from us. I also prepare the SOP for them. All right. So I will end this. Pass to the next speaker.
Thank you very much, Madam Katrina. Very detailed explanation, because we assume you as the subject matters expert.
Correct.
We always refer to you on the theoretical calculation and also
Correct.
hands-on. Next, Mr. Asnizam will present on the maintenance, Katrina, and also how to handle the equipment. Asnizam?
I already unshare, not?
Yeah, okay.
Already, okay.
Okay, yeah. Next is Mr. Asnizam. Okay. Please go on, Mr. Asnizam.
Okay. Can you see my slide? Okay.
Okay.
Okay. Assalamualaikum and good evening. This is the CAN number 14 webinar. My topic today, first ICP OES operation and ICP OES part 1 sample introduction setup and ICP OES part 2 TOSH setup, key element in the TOSH setup, and ICP OES part 3 order command user maintenance task. Okay. ICP OES operation, before starting, turn on the instrument and cooling system, check argon and nitrogen gas supply and pressure, ensure torch, nebulizer, and spray chamber are clean and fitted properly. Step up, warm up the instrument 40 to 70 minutes, ignite the plasma, check the correct color and shape. Calibration, prepare the blank and standard solution, run standard to create the calibration curve, choose correct wavelength and adjust for the interference. Number 4, running sample. Rise system with the acid water before run the sample, run sample and QC check. Watch for the unusual signal and change. Number 5, after analysis, rise the system with the acid water, turn off the plasma and cooling system, shut off the argon and nitrogen gas. And then lastly, to routine care, clean torch, nebulizer, and spray chamber, replace one part when needed, troubleshoot and dig blockage and load signal. This is the video how ICP OES operation. Part 1, sample introduction setup. In inductive coupled plasma optical emission spectrometry, ICP OES, the sample introduction system is a critical first step that directly affect the analytical performance and accuracy. This setup typically include nebulizer, spray chamber, sample uptake tubing, which they work together to convert the liquid sample into the aerosol for the plasma excitation. Proper element, clean component, and correct selection of nebulizer type. Example, concentration, flow, and extra. Instantly to ensure the stable plasma, minimal signal fluctuation, and reduce potential interference. Optimizing the sample introduction, system had to achieve a relation to detection limit, consistent precision, and prolong the instrument lifespan. This is the video how the sample introductions set up.
Hello, my name is Ankit Shah and I'm from Agilent Technologies. Let me tell you a bit about the PerkinElmer Optima ICP OES. The PerkinElmer Optima ICP OES spectrometers are a dual-view benchtop ICP OES system. Agilent now offers a range of supplies for your PerkinElmer ICP OES that are fully qualified and guaranteed to be compatible. This is the first of a series of instructional videos to help you achieve the best performance and productivity with Agilent supplies for your PerkinElmer Optima ICP OES. We will now be introducing the sample introduction supplies, which includes the peristaltic pump tubing, spray chamber, and torch assembly. Fit the bridges or plastic tab of the tubing into the slots of the peristaltic pump. Clamp the tubings, ensuring that each of the tube is centered to the groove. Use tubing with black tabs for the sample and red tabs for the waste. Start the pump and introduce some deionized water. Confirm that the liquid is being evenly pumped into and out of the spray chamber. If necessary, adjust the tension on the clamp until there is a smooth, even flow. Do not over-tighten. The inert Scott spray chamber is used for high dissolved solids and hydrofluoric acid digests. And the glass cyclonic spray chamber is normally used for aqueous solutions and organic solvents. Please avoid hydrofluoric acid digests. Attach the drain tubing to the spray chamber. Orient the spray chamber so the drain connection is facing down. Firmly push the spray chamber into the mounting block. Close and lock the securing clamp. Loosen the nebulizer locking nut. Gently insert the nebulizer into the spray chamber. Tighten the nut. Now, let me show you the glass cyclonic spray chamber. Open the clamp on the glass cyclonic spray chamber adapter. Insert the spray chamber into the adapter and close the clamp. Make sure the spray chamber is pointing downwards to ensure proper drainage. Then tighten the securing nut to lock the spray chamber in place. Attach the drain tubing to the spray chamber. Firmly push the spray chamber into the mounting block. Close and lock the securing clamp. Fit the nebulizer into the spray chamber. Examine the two gem tips in the end cap. Confirm that the tips are almost close to each other at 90 degrees. Confirm that the sample capillary tubing and the 1/8-inch OD tubing for the nebulizer gas flow are securely connected using the ferrule fittings. Moisten the O-ring. Gently tighten the two knurled screws to the end cap. While supporting the spray chamber, position the end cap assembly and gently push and twist the end cap until it sits firm onto the spray chamber. Tighten the two screws. Confirm that the sample capillary tubing and the argon gas fitting is securely fastened to the nebulizer. Loosen the nebulizer locking nut. Insert the nebulizer as far as it will go in. Tighten the locking nut. Please see the other videos in this series for torch installation and general maintenance on your PerkinElmer Optima ICP OES.
This is part 2, torch setup. The torch of ICP serves as a location where the aerosol sample introduced into the argon plasma for atomization and excitation. Correct torch element to ensure the plasma and the positioning of atomium within the spectrometer, optical part, maximizing the signal intensity and minimum background noise. Key point of the torch setup include torch type selection. Standard quartz torch are common, but the high metric sample and a reverse or demotable torch may be used. Injector tube selection. The injector diameter affect the sample flow rate and the plasma robustness. Smaller diameter reduce metric loading, but maybe increase the clogging risk. Torch positioning, fine adjustment is vertical and horizontal positioning as significantly affect the sensitivity and the stability. Maintenance and cleaning. Regular cleaning prevents site deposit and carbon build-up that destabilize the plasma. As well, configure torch system contribute the optimal excitated, especially reduce the interference and improve the long-term of reproducibility of the result. These are the location of the torch inside the machine. This is the example of the Optima torch. This is the video how to maintain the torch and set up the torch.
This is a second of a series of instructional videos to help you achieve the best performance and productivity with Agilent supplies for your PerkinElmer Optima ICP OES. Now, let's look at torch maintenance. Switch the plasma off and open the side door to the sample compartment. Lift the spray chamber clamp and remove the spray chamber from the mounting block. Rotate the torch module anti-clockwise. Using the channels as a guide, carefully slide the torch module out of the plasma induction plates. Press the injector lock on the torch coupler and remove the injector. Loosen the black retaining ring and carefully remove the torch. Inspect all 5 O-rings on the torch mounting shaft and the injector adapter for cracks and wear. If necessary, replace them. Inspect the torch for cracks and excessive wear. Replace if necessary. Remove the copper foil igniter tape. Immerse the torch glassware and injector tube into 5% nitric acid solution. An ultrasonic bath may be used with care. After soaking, thoroughly flush the torch components with deionized water. Allow to dry before reassembly. If deposits persist after cleaning, soak again using a higher acid concentration. To reassemble the torch, Fit a new copper foil igniter tape. Place the white Teflon ring and the black retaining ring on the torch. Put the body inside the torch coupler, making sure the mark on the torch body aligns with the notch on the torch coupler. Tighten the retaining ring. Insert the injector into the torch adapter until it locks in place. Press the injector lock to sit the injector. Make sure the injector tip sits right below the intermediate tube. Align the torch module. Ensure the markings on the outside of the coupler are facing up. The two locking lugs on the inside of the torch coupler are in the east-west direction, and the guide pin is at the bottom. Insert the torch module into the mount so the locking lugs and the guide pin engage the channels. Carefully slide the torch through the RF coil or the plasma induction plates. Rotate the torch module fully clockwise. To ensure proper ignition, turn the torch module an additional 2 mm from where you want to go, and then rotate back the desired position. Verify that the ground pointer is in close proximity to the end of the torch. If required, adjust the ground pointer. Open the spray chamber clamp and orient the spray chamber so that the drain tubing is facing down. Firmly push the spray chamber into the mounting block. Close and lock the securing clamp. Please see the other videos in this series for general maintenance and sample introduction system on your PerkinElmer Optima ICP OES.
Key element in the torch setup, concentric quartz type tube. This housed of the argon flow. Outer tube for the coolant and plasma gas. Intermediate tube or auxiliary argon. Inner injector tube direct to the sample aerosol into the plasma. RF coil encircle the quartz torch and generate the electromagnetic field that sustain the high temperature plasma. Plasma flame and central channel where the aerosol is atomized and excited. Optical part, the emitted light from excited atom to capture and direct toward the detection system spectrometer. Positioning clarity. This clear layout help with element and maintenance tasks by showing how each component interface. Part 3, other common user maintenance tasks. Routine maintenance and centered in the to ensure consistent performance and minimum downtime in SAP, ICP, OES operation. Apart from the sample introduction and touch, user should regularly check the service other system components. They are peristaltic pump tubing, inspect the wear, flattening or crack, replace regularly to maintain the stable sample flow. Argon supply and regulator, monitor cylinder pressure, check for leak, and ensure flow rate meet instrument specification. Drain system, clean waste line and water to prevent blockage and contaminate backflow. Optical window and viewport, keep clean to avoid signal attenuation caused by dust, salt deposit, or carbon residue. Cooling system, for system with recirculating chiller, maintain cooling level and cleanness to prevent overheating. Daily maintenance check, run standard solution to verify instrument calibration, detection limit, and stability before analysis the sample. Consistent enhance to this maintenance task help to extend component life, reduce operation issue, and ensure accurate, reproducible analysis result. This is the last video for common user maintenance tasks.
This is the last of a series of instructional videos to help you achieve the best performance and productivity with Agilent supplies for your PerkinElmer Optima ICP OES. Let's look at the maintenance of the axial and radial windows. You must remove the windows to clean or replace them if there is a noticeable buildup of deposits or they are etched. Switch the plasma off and open the side door to the sample compartment. Remove the sample chamber and the torch module together. Remove the screws holding the shear gas nozzle assembly. Carefully move it to one side. Carefully unscrew the axial window mount. Remove the O-ring that holds the axial window. Remove the window. Unscrew and remove the radial window retaining ring. Lift the radial window and O-ring out of the mount. Inspect the windows. If the windows are scratched or badly etched, replace them. This degradation may not be apparent, but you may notice a drop in UV performance. Soak the windows in warm solution of dilute nitric acid for about an hour. Rinse the windows thoroughly with deionized water. Allow to dry. Refit the O-ring into the mount. Place the retaining ring loosely over the mount. While holding the window carefully, push the open end of the cylinder through the O-ring down to the base. Screw the radial window retaining ring onto the mount. Hand tighten firmly and do not over tighten. Refit the window into the mount. Check for the O-rings for any wear or cracks and replace if necessary. Fit the O-ring that holds the window in place. Screw the window mount into the snout. Again, hand tighten firmly, do not over tighten. Replace the shear gas nozzle assembly. Screw the retaining plate in place carefully. Replace the torch and the spray chamber assembly. Check the air filters regularly. For the RF generator air filter, remove it from the back of the instrument. If found dirty, place it in a bath of dilute detergent. For the air filter, remove the filter and if found dirty, replace it and refit. Ensure the clean RF generator air filter is dried before refitting. Please see the other videos in this series for torch maintenance and sample introduction system on your PerkinElmer Optima ICP OES.
Okay, that's all. Thank you.
Thank you, Mr. Azizam. For your information, Mr. Azizam is the PIC who handles, who conduct more on the maintenance and also conduct the testing in car. So we almost reached 5 p.m. Now I would like to open any questions since we have the expert, subject matter experts on the ICP OES. Anyone have questions? Or later on, maybe you can put your question. If you have any question later on, you put in the chat box and we will try to assist you on the question arising. Anyone?
Okay, I have one question.
Yeah,
And then
go on.
okay, thank you for the presentation. I have one question to Madam Katrina.
Yes.
Okay. Hi, Katrina.
Yeah.
Okay. All right. So if let's say we have one metal strip and we would like to check on the purity of the metals. Okay. So we can proceed with the SRF and also for ICP OES as well.
Okay.
Okay. And then from your experience, what is the how to say the drawbacks if let's say they claim the purity of the purity of the metals is like 90%, more than 99%. But then when we check from the ICP and we perform the dilution and we calculate back on the percentage of metals available in the solid sample, then we find out that the percentage is only roughly around 70%.
Okay, wait. So, Sheila,
Yep.
in terms of purity tests, in the whole world,
Mhm.
the way of analysis is the other way around. Okay.
Okay.
So let's say I have aluminium wire. So my testing is not on aluminium. My testing will be the impurity test for aluminium and follow the ASTM method. So every alloy, whatever alloy they have, they want to do the testing for the impurity. You are not doing the aluminium. You're not doing the major element. You're doing other thing. For example, if I have a gold, they want to know the purity of gold. I did not run gold. I run other. Then 100% minus the others. You understand?
Understand. If let's say, because they are not sure what is the elements impurities available in the
Oh,
in
no,
the
they cannot be not sure because all purity matter do have their spec one. I mean the whole world will do like that. You understand my meaning?
Understand.
They cannot be not sure. Maybe you're not sure, but the person who would like to send
The sample?
the sample, they
Uh-huh.
must be sure. For example, because actually there is high purity analysis for material. They have many standard to follow one. You get my meaning? For example, maybe I give you some idea.
Okay.
So we actually your sample is a alloy method, metal, more
Is
metal,
a metal strip.
metal strip. So you see, I give you some idea to talk to them. For example, I share. So let's say this is a gold. ASTM method for gold.
Okay.
52562. So if you gold of 49, 39 or 29. So when you say you want to ask me to test whether your goal is 99.5 or 99.95, so the element that I test is copper, palladium, iron, lead, silicon, and so on. This element. If you are in US, you also do this element. You're in Australia, you also do this element. It's understandable. The person we had to we had to trust whatever the person say. They are already 99 point something, but whether how many nine is it 29 or 3N or 5N or 4N. So is this are the method that we test.
Okay, so we are not looking for the main element. We are checking the traces impurities.
Yes, correct. So that is gold. For example, there's others also. There are other things also. Let's say in the battery material also same. You are doing the other way. For example, let's say you have this is a silver. They claim they are silver, pure silver ingot. So you are running copper, lead, iron, SB, selenium, Te, Bi, and palladium. Whole world will do the same thing.
Understand. Is there any standard method that in terms of purity
No,
is there any
you had to find. So it's everything they are tested. Whole world is going to test the same thing. This is aluminium, pure aluminium. These are the elements they are looking at. If you are pure copper, they also have an element of this is the element they are looking at.
This is for pure copper. Do you have
Pure copper? Pure
okay.
copper. Then
Okay.
many more. So you understand? This is a pure zinc. This is a pure zinc. So if you say you are zinc, you are running this element.
Okay. Noted,
So
cikgu.
okay. That's all.
Okay. All right.
Okay.
Thank you.
Okay.
Thank you, Madam Katrina, for the explanation. I have provided the QR code and also link for your feedback for our improvement. So any more question? We almost reached 5 p.m.
Excuse me. Hello. I have one question.
Yeah, please. What is Suzaini?
Miss Katerina, to Miss Katerina, because you are talking about the aurum just now, the goal. If let's say the situation is actually if I have some sample that are coming from the nature that are having like aurum in very low concentration, is it possible for us to detect using the ICP OES? Because
Yes.
as far as I know, we can do the calibration curve, it's detectable, but then in terms of the real sample, we are having very low concentration of the aurum or gold. So how come is there any suggestion for us to overcome the
No, your goal is in what? In soil?
in soil? Yeah. Let's say in soil. Yeah.
In soil. So when you say low, how low is your goal?
It's actually it is unknown. But then for me, I tried to search for any common concentration range in the potential or aurum concentration in some clay or soil. It's actually maybe around less than 10 ppm, less than 5 ppm. So it's very low because we need to do the digestion first, and that's also will cause for the dilution factor and reduce more concentration. So, is there any way that for me to find like a method
In
to
ICP
detect?
OES, Nizam always can plot calibration curve for gold, 10 ppb. The lowest point is 10 ppb,
10
50
ppb.
ppb, and 100 ppb. No issue.
Oh, so
Just that
the
you need
LOD
to
is
make
actually
sure.
up to ppb. It's actually up
ICP
to
OES is double digit ppb.
double digit ppb. Okay.
So meaning that if you have ICP OES, most of the element you can run 10 ppb. Not sulfur sulfur is UV. Sulfur is much more difficult. Most of element you can run 10 ppb, 20 ppb, or 50 ppb, 100 ppb. It's not an issue. So now you need to get your sample fully digest. That's all.
All right. So it can go down to 10 ppb lah for the
Can.
calibration curve. I thought it's actually within upper than 1 ppm. So
No.
okay.
He can
Noted.
plot 10 ppb. That means if 4 point 10, 20, 50, 100 for your sample that's very low.
So I mean
No issue.
ICP OES is capable lah for the ppb level.
This is a common for a lot of metal recycling company. Metal recycling company now they are not doing they are doing urban mining. Urban mining means they mine the gold, palladium, and PT for all the electronic waste.
Yeah.
So all of them blocking calibration curve because the electronic have the gold but not so high.
Yeah. Okay. Noted.
Okay.
Thank you.
Okay.
Madam Katrina, one
Yeah.
question from Dr. Nozato Shima. Do REE is only suitable to trace using ICP-MS.
Yes, ICP-MS only.
ICP-MS, yeah?
Because why? In ICP OES, the wavelength of rare earth is a lot, and ICP OES has much more complexity of the wavelength overlapping. They overlap each other more. If just now I show you MS, there are problem like that. Maybe they will have 20 over problem, but ICP OES, your problem much more chaotic. So rare earth must use the ICP-MS, really.
Okay, hope that answering Dr. Nozatushima question.
But actually, your ICP-MS is not Perkin Armour. It's very sad to know that. Right?
Because we are using the video through Mr.
No,
Azizam slide.
the video. Your ICP-MS at the UTP.
I'm going to relate the video because we are using the 8000 series, Katrina.
Yeah,
Maybe the Dr. Nozatushima is a different brand, I think.
No, ICP-MS, the rare earth
Yes.
is using ICP-MS.
Yes, Madam. Yes, Madam Katrina, the ICP-MS in UTP
Yeah,
is
other brand.
not. Yes.
Because I running rare earth many years already for Linus, for many ICP-MS in purchase is for the rare earth analysis. So I really know it's not a very simple task.
So we can refer to you lah, because you have the experience to running the sample.
But you are not buying Perkin Armour, I will not able to guide you. That's why I said it's so sad that you all do not have Perkin Armour ICP-MS. Just now for the question you asked about rare earth. It's okay.
Okay. Right. We already past 5 p.m. Maybe next session for the ICP-MS topic or the under your expertise, we might discuss with you again for the other webinar series, Madam Katrina. Thank you so much for your time. So, all right. Right. So with that, I would like to thank you very much for the attending this webinar. My apology for the technical problem. So anything you have problem, you might contact me, Madam Hasila, our chemist, or Mr. Azizam for the testing. But usually, students or researchers will discuss first with Mr. Azizam on the suitability before we conduct the testing of ICP-MS. With that, thank you very much. Thank you very much for your time. Right, thank you.
Thank you. Bye-bye.
Bye.
Okay, bye.
Bye.